Hi, welcome to Team Counsel's final design review presentation for our project, Zephyrus, a retrofire deorbiting unit. As an introduction, the accumulation of so-called space junk poses a major collision hazard to actively operating satellites around Earth. It also increases light pollution and poses an additional hazard in the form of the possibility of space junk entering an uncontrolled re-entry into the atmosphere and impacting the Earth's surface at a point that we may not want it to, for example, habited areas. This problem is compounded by the fact that space exploration is relatively young. Awareness of the problem as well as solutions to this problem are still somewhat scarce. Nevertheless, there are multiple proposed solutions by this point. Models range from preventative to retroactive. Solutions also vary in the results that they propose. Some solutions propose to deorbit junk and send it into the atmosphere for burnup or to impact the Earth at a designated point, or to send junk into even higher orbits known as graveyard orbits. Likewise, the mechanisms proposed to achieve these ends are also very diverse, ranging from the use of solar sails and solid rocket motors for propulsion to the use of magnetic tapes or nets for mechanisms to capture space junk. Our problem is as stated, and essentially the solution that we propose is a preventative one. So we propose to deorbit future satellites using an independently operating manned deorbiting unit. This unit is to be installed on our satellite prior to launch, and at the satellite's mission end of life, the unit will be used to pilot the satellite into Earth's atmosphere for burnup. So essentially, the unit is always going to be attached to the payload, which is the satellite. The unit will be going up with the satellite during the initial launch from Earth's surface, and when the satellite becomes defunct or decommissioned, the unit will be sending the satellite to its death. So all parts of the mission should burn up together, both the deorbiting unit and the satellite itself. We have chosen cold gas thrusters as our means of propulsion. This was the result of a multitude of considerations. We found it to be a decent balance between cost, overall mass, launch fuel costs, etc. Our intended targets are small satellites, less than 200 kilograms in mass, and these are to be in low Earth orbit, which is less than 1,200 kilometers from the Earth's surface. So a little bit more about our reasoning here. At 600 kilometers of orbit, or 600 kilometers of altitude, it would take roughly 10 to 25 years for a satellite at this orbit to naturally re-enter Earth's atmosphere and burn up. Our unit will deorbit this hypothetical satellite from 600 kilometers down to 400 kilometers, which at this point the satellite will be able to passively enter the Earth's atmosphere and burn up within approximately 1 to 5 years. Our cold gas thruster system consists of 4 main subsystems. So these are our tank, our chassis, our nozzle, and our controls. The overall dry mass of our system is 80 kilograms, and it is designed for a target payload based on OneWeb's individual unit specifications for their future satellite constellation launch. So these are roughly 1 by 1 by 1.3 meter payloads. So here's our system overview. As you can see here, we have our nozzle on the outside. We have our chassis face plates. We've milled hexagonal patterns into each of these face plates for weight-saving purposes. Inside, we have our spherical tank, which is using passive mechanisms to respond to loss of pressure as we dispense gas out through the feed line and through the nozzle into vacuum. And then we do have our feed line present here as well, visible in the cutaway as part of the internals. You can also see here our valve, which is controlled by a solenoid for accurate and consistent release of gas.
These are the design specifications for the tank subsystem in our cold gas device. The first is that the tank must hold enough gas in order to perform the deorbiting maneuver, plus an additional 20%. This 20% is due to the potential of non-ideal conditions found in the real world, such as non-instantaneous velocity changes and the chance that the satellite may be at a higher orbit than initially calculated for. In addition, the OneWeb satellite that we're basing our device off of has a estimated weight range of maximum of 200 kilograms. The analysis was performed at 180, but we wanted to make sure that we could potentially perform the maneuver if it was at the high end of that weight estimate, and 20% was enough to account for that. The tank must also securely mount within our chassis, so it fits within the box itself, and there's still room for the plumbing. And the pressure should be known as the gas leaves the tank. This pressure will then be used to calculate uh, further delta V from our controller to make sure we're turning the nozzle on and off at the correct time. There should also be a mechanism that allows us to fill the tank once it has been mounted inside the chassis. This is an overview of the tank. It has an inner diameter of 0.28 meters and a thickness of 0.01 meters. It has a ring that is connected about a little bit above the uh, equator of the spherical tank. This is because these tanks are typically manufactured by welding the two halves together, and so we didn't want it to be exactly at that line, so there was still room to weld. Then it makes use of a mounting ring that connects to the tank through 8 3/4 inch hex bolts. This type of design can be seen in other industry tanks, and it's typically the tabs connected around the spot is what is seen. The tabs then have 4 holes on each tab that can then be attached to mounting brackets within the tank that allow it to actually be mounted within the chassis itself. So some analysis that was performed in the creation of the tank. The first step was to figure out the total delta V moving between 600 kilometers to 400 kilometers using the Vis-Viva equation. Once we knew the delta V required to make that change, we then used the rocket equation to figure out the total amount of propellant we would need. In this case, it's nitrogen. That is about 45.5 kilograms. After that extra 20%, we're looking at 54.6 kilograms of nitrogen. So once we knew exactly how much nitrogen we were using, we could then use the ideal gas law to estimate the total volume that would fill. And this led to the tank with an ID of 0.28 meters that we had previously saw. Next, there was analysis on what the temperature of the tank would be at. This was used, a solar exposure time of 63% was used. This basically means that in a 90-minute orbit that the tank experiences, it will be in the sun for about 60 minutes of that time. It then absorbs energy from the sun itself, from the earth, and then from the sun reflecting energy off the earth. This leads to a tank temperature of 373 Kelvin to 384 Kelvin. This range is due to the inherent solar flux range, and it can be considered to be the mean temperature of the tank throughout the whole entire orbit. From there, the ideal gas law was used to estimate, find a more accurate number for the tank pressure range, and this was found to be 49.5 to 51 megapascals. So next we can compare the design of our tank to the requirements that we previously listed. So the analysis proved that the tank can hold enough gas to successfully perform this maneuver in addition to that extra 20% gas. The tank can also be securely mounted within the chassis using this mounting ring. The tank can be filled using a latch valve fill valve mechanism. This is when the latch valve is closed and the fill valve is opened. The fill line can then be connected to this fill valve and you can begin filling your tank. Once your tank is full, you can close the fill valve and open the latch valve, and you know that all your gas is filled within the tank. Next, we have a pressure transducer that comes directly as the gas leaves the tank. This will allow us to measure the pressure so we can make sure we have it for further calculations. Some future work that we would like to do on the tank. Late in design, it was found that at 50 megapascals, nitrogen is in a supercritical state, which means it could act as a liquid, and basically that this pressure is way too high. So ways to mitigate that is a white zinc oxide coating can be placed on the tank and it will drop the tank pressure to 35.5 megapascals, and it drops the temperature by about 100 Kelvin. So this is a pretty significant drop, and it makes it to a lot more reasonable pressure range. Uh, so one question is, why didn't we implement that immediately? Well, because it was found so late in design, if we were to drop to this lower pressure, it would require a resizing of the nozzle, a recalculation of flow rate, a recalculation of total burn time, and there was a lot of factors that would then be changed. So instead, it's something that we can consider for future analysis on a potential second iteration. Another thing that could be done is a more comprehensive analysis on the stresses experienced by the tank. So it was assumed that this tank would contain a composite wrapping. This is something that most gas tanks that go to space have. However, the exact effect that it has on increasing the tensile strength wasn't something that we had any experience calculating, so we decided to treat it as a black box and assume that the tank could handle any pressure. This was not a good assumption as it led to this supercritical state error, and in the future, we should have a better understanding so we can make sure we correctly calculate what those stresses will be.
All right. So the design specifications of the chassis. So we decided that the mass of the entire Zephyrus chassis with the propellant should not exceed 180 kilograms, as to not double the launch cost of the system. This essentially means that the launch cost of Zephyrus should not exceed $5 million. In addition, because of the way the satellite is built, the chassis itself has to fit in a 0.8 meters by 1.3 meter rectangle, as it needs to be sat on top of the satellite. The chassis itself needs to be large enough to house the 0.3 meter diameter spherical tank along with necessary plumbing and electrical components. And because the propellant weighs around 54.6 kilograms, the chassis, along with the tank and its internal components, should not exceed a mass of 125.4 kilograms. The walls of the box need to be light enough while maintaining structural integrity to withstand the launch forces and support the weight of the external multi-layer insulation that will protect the internal electronics and plumbing from radiation. In addition, because of the necessity of exactness in space, the tolerances for each part of this design will have to be within 0.000254 meters. So this is our chassis without any of the internals inside. The dimensions of it are 0.75 meters on lengthwise, 0.45 meters height-wise, and 0.45 meters width. The material used for every single part of the chassis build is aluminum 7050 because it is corrosion resistant and very aerospace friendly. Without any of the internals, the mass of all 6 plates welded together are 57 kilograms, and on the outside of each plate will be multi-layer insulation. To reduce the weight in the chassis, we implemented a hexagonal pattern. The hexagons were built around a circle of 4 centimeters in diameter. This entire design is 0.02 meters from the edge of each box. The vertical distance between the hexagons, which is this distance right here, is 5 millimeters, and the distance between each of these individual shapes is 2.5 millimeters. This is the top plate. The dimensions of the top surface, this right here, as it is a trapezoid, is 0.71 meters by 0.41 meters, while the bottom is the same as the chassis box, which is 0.75 by 0.45 meters. The plate itself is 2 centimeters thick, and because it is aluminum 7050, has a mass of 10.98 kilograms. The angle cut here for the trapezoid is 45 degrees. This is the side square plate. At the top surface here is 0.41 meters by 0.41 meters, while the bottom surface here is 0.45 by 0.45 meters. The thickness of the plate is 2 centimeters with a mass of 6.5 kilograms. This is the long side plate. Similar to the top side plate, it has a top surface of 0.71 meters by 0.41 meters and a bottom surface of 0.75 by 0.45 meters. It has a thickness of 2 centimeters. And because there's no nozzle hole like there was for the top plate, the mass is a little heavier at 11.3 kilograms. This is the bottom plate. The dimensions of the top surfaces and the bottom surface are the same as the other previous long side plate and the top plate. However, the bottom plate has 4 distinguished bolt holes, as you can see here. And this small hole here will be for the electrical wires to connect to the satellite. So each bolt hole is around 5 centimeters from each edge. So this is 5 centimeters, this is 5 centimeters. The bolt diameter itself is 1 inch. And the electronic box was designed to be 0.09 meters by 0.1114 meters. And it is built centered around this electrical hole where the wires will connect to the satellite. Each of these individual squares will be the bolt holes to where the controllers are bolted into the chassis. Those bolt hole diameters are 5 millimeters, while this electrical wiring hole is 1 centimeter diameter. All right, in order to mount the tank assembly to the chassis, we decided to go with the tank mount bracket with a trapezoid design. These small rectangle sides here on the side will be welded to the chassis itself at a 45-degree angle. The top surface is 0.06 meters by 0.143 meters, and the bottom surface is 0.06 meters by 0.173 meters with an angle of 45 degrees. The thickness of this bracket is about 1.5 centimeters, and these bolt holes in the set are about the center, and they're ½ inch in diameter. There's 4 of them, and each has a mass of 0.38 kilograms. This is going to be the electronic box that we use to store the controllers. It is made of aluminum 7050. This is the lid. It has a dimension of 0.09 meters by 0.1514 meters. It has a thickness of 5 millimeters. Each of the bolt holes are in the corner. They have a diameter of 1 centimeter, while the center hole is for the wires to connect to the pressure transducers and the solenoid. It also has a diameter of 0.01 meters. It has a mass of 0.19 kilograms. This is the mainframe. This itself will be welded to the previously aforementioned location on the bottom plate. As the bottom surface here has dimensions of 0.09 meters by 0.1114 meters, while the top is 0.09 by 0.1514 with a thickness of 0.005 meters. These bolt holes are within platforms that are 2 centimeters by 2 centimeters, and the diameter of the bolt hole is 1 centimeter. Overall, the mass of this item is 0.17 kilograms. To insulate our entire chassis, we have decided to use multi-layer insulation. It's an industry standard and will be applied externally to the chassis. This will protect the internals from radiation and thermal escape. The mass is going to be about 1.2 kilograms per meter square, and after taking the surface area, we're going to need about 2.10 kilograms of this multi-layer insulation. So this is the final assembly. As you can see, the tank is welded to these brackets here with a complete plumbing system. The nozzle is welded to the top plate, and this is our controller box. And as you can see here, it perfectly fits onto the top side of the satellite, indicating that we have met our design requirement. So when comparing our design outcomes versus the requirement, so the requirement was the wet mass of our entire system is less than 180 kilograms. The final wet mass was 133.5 kilograms, which meets the requirement. We also have a requirement where the launch costs do not exceed 5 million. Taking the range of the Soyuz rockets, it costing $20,000 to $30,000 per kilo. We can see that the launch costs are under 5 million, where it ranges between 2.67 million and 4 million. One of the other requirements was to fit within that 0.8 meters by 1.3 meter rectangle, and the box is 0.75 by 0.45, which easily fits into that surface. The tank with a 0.3 meter diameter is a spherical tank, needs to fit comfortably inside, And because of the 0.45 meter by 0.5 meters, the tank comfortably fits inside. And because of the hexagonal design, each of the plates itself are lightweight but have structural integrity. Due to lack of time and a lot of scaling down of our system, we ran out of time. So we will, in the future, we'd like to do more in-depth strength and stress analysis on these welds here and the plates themselves, and more in-depth temperature analysis to see if the insulation actually works, and possibly we can find ways to further reduce the weight where possible.
The nozzle that we chose to go with was the convergent divergent profile, and this profile utilizes a subsonic to supersonic airflow, and it essentially is a tube that gets choked and then expands infinitely. So there's a lot of pros and cons that come with this nozzle. One of the main pros is that it's cost efficient in design and low in weight. And that is because the design is very simple and it has a very hollow profile. And then the cons is that because it's simple and that there's not a lot of flexibility that comes with it. We're not able to use this nozzle to alter the flow rate, and that will require more from the system and more accuracy from the system to feed it the right pressure to achieve the right flow rate. Other nozzles that we're looking at were the plug nozzles and the conic nozzles. In the right-hand corner here is an example of a plug nozzle. We decided not to go with this because you can see that there's internal components, and we thought that with multiple nozzles, there would be extra weight that we wouldn't need compared to the convergent divergent nozzle. So the material of choice for this nozzle is the aluminum alloy 7050. We were deciding between the 7075 and the 7050 alloy. And the reason we went with the 7050 is because it exhibits the same tensile strength, but it has more resistance to corrosion. The only benefit of the 7075 is that it's about 30% cheaper than the 7050. But we really value the resistance to corrosion because our system is designed to be used after the satellite's life, which can be anywhere from 5 to 25 years. And it's very important for the design to remain durable and usable after all those years. In the bottom right-hand corner, there's also the tensile strength and yield strength of the material. For the nozzle, here's to further validate our choice of material. The temperatures that we're dealing with are negative 107 degrees Celsius to 123 degrees Celsius. Also mentioned is that many of the components in our system will be using the same material. Here on the left is a 1D diagram of how the path from the tank to the nozzle will be. And then in the middle is the CAD version of our internals. And on the right-hand side are the more significant components in the diagram. As you can see from the tank, it goes to the fill valve and the latch valve, and in between there's a pressure transducer for backup purposes. And then it goes to the solenoid valve, where there's a pressure transducer before that to measure the pressure that will be going into the nozzle. The internals, going into the different components. We're using very high quality components because we're dealing with a very high pressure of around 7,000 PSI. But the difference is the solenoid valve, the fill valve, and the latch valve. We decided to go with different valves because the solenoid valve is dealing with a high pressure and the fill valve and latch valve is dealing with less pressure for less duration. For example, here, for the latch valve and fill valve here, it would be only used and it would only close when the user needs to feed tank more gas. And then the solenoid valve, which would be normally closed for maybe up to 25 years, is dealing with that pressure for a very, very long duration, which is why we need a more quality valve for that situation. Most of the plumbing will be utilizing a 19mm tubing, and that's around 3/4 inch for the whole system. For the pressure transducer, we found this industrial one that is very high in accuracy, and it's able to withstand ranges of -45 to 120 degrees Celsius, which is perfect. It's not near the lower range, but this is in the internals of our system, so it won't be exposed to as extreme temperatures. And it's also able to measure really high PSIs, which is what we need. And here, the placements of our, for each component. This first transducer may be redundant, but it acts as a backup, as I said earlier. And that is because if this one fails, then we still have this one. But then it's also placed at a very strategic point. For example, the solenoid valve is placed very close to the nozzle because when pressure travels, it may diminish. So we have it as close to the nozzle as possible so that when the transducer is measuring the pressure, we know that the pressure that reaches the nozzle is very, very close to what we measured. And here are the direct costs of each components. So for the company, SA Materials, they sell piping for around $300 and they custom link size it for $120 for that's including all the different components here, which is around 4, 5, or 6 components. And for 2 components in our design that cannot be just retail bought is the hexagonal design, which will Justin will show later in the slides. It's a very unique design and it cannot be bought retail. So the idea here was to buy 6 plates and have a company mill those designs in. And this aluminum alloy is very, very strong, so you needed a company to deal with this. So Superheat, they charge anywhere from $100 for a small design to $200 to $2,000 for bigger millings. And I think it's going to be an upper spectrum because our hexagonal design is all over our plates on both sides. And the good thing about this company is that they perform stress simulations and stress tests after their finished design, which is very important because even a little bit of error can cause the hexagonal design to not do its purpose because it's very thin and it's meant to be very strong and maintain its structural integrity, but a little bit of error can get rid of all of that. 7075, as mentioned earlier, was cheaper. Our design uses completely 7050, but that is a consideration that could be used for internal where corrosion is not as likely to happen. The nozzle, we weren't able to, we contacted multiple companies and they didn't get back to me, but looking at other projects, the nozzle can vary around $2,000. And then here are the other prices for the solenoid valve, the latch valve, and the pressure transducer. Here, there's the stress test for the hex plates. In the left-hand corner here, we have just pressure, and then the right-hand corner, bottom-hand corner, we have pressure plus temperature, and then on the top is just temperature. As you can see, there's no critical failures, and the fixed geometry is all on the edges where the plates will be welded to the rest of the box.
Another important part of the system is the orbital transfer mechanism design. The aim of our project is to shorten the fall time of dysfunctional satellites by using active cold gas thrusters to lower the altitude of the target satellite. To specify, we aim to bring the target satellite from an orbital height of 600 kilometers to 400 kilometers, and we aim to keep the error of the final orbit height within 5%. The total mission time is not the uppermost important thing, so we set a tolerant limit of 2 hours. The method of lowering satellites' orbital altitude is the Hohmann transfer, which uses an elliptical orbit to transfer between 2 circular orbits of different radii around the same central body in the same plane. Other orbital transfer trajectories considered included bi-elliptical transfer and other faster transfers. However, since the project prioritizes minimizing cost and fuel over having shorter mission lifespan, the Hohmann transfer is the most reasonable choice as it is the most energy-efficient transfer method. The working principle behind the Hohmann transfer is that decreasing the velocity of a spacecraft means reducing its specific mechanical energy, which in turn decreases the length of its semi-major axis around the central body, which is the Earth. During the Hohmann transfer, to move the target satellite from a higher orbit to a low Earth orbit, it must travel along an elliptical intermediate orbit called the transfer orbit. The Hohmann transfer orbit consists of 2 steps. As shown in the figure here, in the first step, the satellite in orbit 1, which is the higher orbit, uses the cold gas thrusters to decelerate by delta V1 and enters the elliptical transfer orbit. When the satellite reaches perigee of the transfer orbit, it uses the cold gas thrusters for the second time to decelerate again by delta V2 and enters orbital 2, which is the final lower orbit. One of the important caveats of the Hohmann transfer is that it assumes instantaneous changes in velocities, meaning that the satellite needs infinite acceleration and infinite thrust force. As unrealistic as it may sound in the first place, this assumption is commonly used in the industry and is well justified by many papers and projects. The error of this assumption is indicated by the ratio of the total burn time over the transfer orbit's time of flight. In our case, the total burn time is below 20 seconds and the TOF is above 2800 seconds, meaning the error of analysis is well below 1%. We will further justify the validity of our assumption using the physical simulation. To simulate the orbital change, the General Mission Analysis tool, also called GMAT, is used. GMAT is an open source software system developed by NASA for space mission design, optimization, and navigation. Comparing to the other simulation tools, GMAT was chosen for its reliability and full support of real-world models. In GMAT, we first set the thrust force to be 1780 newtons and the specific impulse to be 73.5 seconds, which are the estimated values from the previous sections. In this figure, we can see that the radius of the perigee and apogee initially oscillates around 600 kilometers. After the orbital transfer, they drop to oscillate around 396 kilometers. Comparing to our goal of 400 kilometers, the error is 1%. Note that we're using an estimated value for the thrusters, which is calculated from the pressure of the tank and other parameters. We are well aware that our estimation may not capture some of the factors that have a big impact of the actual thrust force, including loss of pressure from plumbing and error in the gas pressure. In most similar systems, it is very difficult to address all the factors, and the proper way to determine the thrust force is to directly measure from the nozzle. And to account for this uncertainty, we redid the simulation with the thrust force set to be half of the original value, which is 890 newtons. And we set all the other parameters to be the same. The satellite also drops to around 396 kilometers, which also has the same error of 1%. So the physical simulation in GMAT has demonstrated that the thrust force ranging from the estimated value of 1780 newtons to half of the estimated value, the Hohmann transfer algorithm successfully brings the satellite from an altitude of 600 kilometers to 400 kilometers within an error of 1%. The total mission time is the transverse orbit time of flight, which is 2,840 seconds. The design fully achieves the goal of lowering the satellite's orbit height within a reasonable amount of time.
Now it comes to the part of the valve controller. The design specification of the valve controller is that the controller will be implemented on satellite's computer in Python. The input is the real-time tank pressure, temperature, satellite's velocity, as well as the satellite's altitude. And it outputs a time sequence containing the control signals of our valves, basically just the digital on and off signals. And the system design and analysis part includes thruster force calculation, controller implementation, as well as the coded simulation. Firstly, we calculate the exit velocity based on some parameters, including the tank pressure and tank temperature. The throat area and mass flow rate is calculated. And based on our theoretical change of velocity value, we can find the burn time, the total burn time, and finally obtain the thruster force. And for the controller implementation, currently the model does not equip sensors like altimeter, thermometer, and gyroscope, and it is not feasible to obtain this real-time data from our satellite in simulation. Therefore, black box is chosen to represent our input data. The main algorithm follows the Hohmann transfer to deorbit the satellites twice based on previous analysis. After the valves are open, the controller continuously monitors the velocity and calculates its change. The time step we chose is 0.1 second. Once the change reaches our theoretical value, the valves are closed. For the second deorbiting, the valves need to be opened at the perigee. A threshold value is chosen based on the error of the altimeter in order to detect whether the satellite reaches the perigee. And for the coded simulation, the coded simulation is created for testing the controller. This coded simulation is based on theoretical equations described in the thruster force calculation section. The velocity data is simulated by physical equation below. And Other unavailable real-time data is also simulated, either by adding some noise to a periodically constant value or by calculating the physical equations. The noise is simulated by randomly choosing values under normal distribution with certain mean and variance. For example, when simulating the pressure noise, the mean of the normal distribution is taken to be the average between the maximum and minimum value of the tank pressure. The standard deviation of the normal distribution is taken to be the difference between the maximum and minimum value of the tank pressure divided by 4. Because 4 standard deviation centered as the mean captures 95% of the data. And the plot is the output of the controller. According to the results, valves are open for 18.8 seconds, which reasonably matches our theoretical calculation of 18.324 seconds. Based on the plot of the time sequence, the satellites needs to wait for approximately 2080 seconds before the second orbital transfer process. And the open time of the valves can be considered as instantaneous in comparison with the total time the satellite requires to deorbit.
As for the design specification of the electronic circuit control circuits, it must be able to convert the digital input from the satellite's computer to the digital output connecting to the solenoid valves, controlling the open and close of the solenoid valves. Successful design should include the components that are able to work in a relatively extreme condition in the space, and customized parts might be required for this purpose. This is our circuit, and it connects the digital input from the satellite's computer to the solenoid valve. We basically just use a relay module in between, and output power will be from the satellites. The relay module works on the 24 volts voltage, while the satellite is providing an unregulated voltage of 22 to 38 volts. So we need a voltage regulator in between to convert the voltage output from the satellites to the relay module. 2 capacitors here are connected to the input and output of the regulator to smooth the voltages. We also choose the solenoid valve that's working under 24 volts, so that we only need 1 voltage regulator, saving us some mass, which is highly desirable in space applications. The design was based on the assumption that the satellites can provide a reasonable digital input as the control signal to the relay module, because the specification of the ports on the satellite computer cannot be found. We also use multi-layer insulation to protect the control component, the electronic components, to make sure that they're able to work properly in the space. So the next part actually includes the work that has been done during the first half of the quarter, but we were not able to finish them. So we still consider them to be highly valuable for future improvements in the design. So we decided to present it here. Initially, our design was with 8 thrusters, just as this picture shows. And our goal was to first change the stance of the satellites so that the face of those 4 thrusters on the top is aligned with the direction of traveling before we actually fire them to decrease the velocity of the satellites. We mathematically formulate our system with states like this. We have 3 translational displacement, we have 3 translational velocity, we have 2 normal uninormal vectors pointing out of the top surface and the front surface. We also have 2 angular velocity that's around those 2 normal vectors. So our goal is to change the orientation of the satellites so that the top surface normal vector is aligned with the direction of traveling. We also have an rotational matrix, and we were trying to multiply this rotational matrix with our current position to obtain the position after rotation. And we done more analysis on that, and we finally implement our analysis in the Python. And actually our simulation results was quite good. But one thing we missed there was that our math was actually too simple. We oversimplify things. We figure out this when we actually do the Webots simulations. So our Webots simulation was trying to simulate the thrusters influence on the satellites. Based on our analysis, we were expecting that when we open the thruster 5 and 8, it should rotate around the vertical axis, but it turns out that it's not rotating like that. It's rotating it this way. After extensive investigations on that and consulting with professors and TAs, we found that the problem here was that we oversimplified the rigid body motion, and the moment of inertia matrix was actually more complicated than we thought about it. So we finally decided to directly use the changing stance function of the satellites, as every satellite is actually equipped with it. And we built our robot only for the deceleration process. So this changing stance work became our future work. And
This is basically our presentation. Thank you for your patience.